Thank you. So welcome everyone to this webinar. Today we are having the second day of this FaMIVE webinar. FaMIVE refers to failure mechanisms, identifications, and vulnerability evaluation. Yesterday we had a very interesting presentation by Professor Dina and by Professor Ariana, in which they both showed how FaMIVE start, what are the main objectives, and what can be done using this methodology, and also the new FaMIVE shell that has been developed recently was presented, and how it is possible to use it so in new applications. So today we have also a very exciting schedule. We will start first again with Professor Ariana Guardiola. She will give this session that is titled Seismic Risk Assessment for Urban Heritage, Pla del Remei area in Valencia. So as you already know, for the ones that connected also yesterday, Ariana Guardiola is a professor in Universidad Politécnica de Valencia in the School of Architecture. She has been working around built structures and how to preserve them. And in particular, Ariana has been leading all the implementation of the FaMIVE shell that we discussed yesterday. And today she will explain this specific case study in Valencia to show how this can be implemented in a specific case. Then we will have two sessions from our colleagues from University of Naples, Federico II. So we will have the first session that is titled Probabilistic Fiber-Based Macro Element Analysis for Global Seismic Response and Fragility Assessment in Masonry Buildings. This will be delivered by Professor Fulvio Parisi. He is an associate professor of structural engineering, and he's also the coordinator of the master's program in forensic engineering at the University of Naples, Federico II. He has been researching in different areas of structural engineering and structural rehabilitation, specifically for masonry and reinforced concrete buildings. And after this, we will have a second session that is titled Integral In-Plane, Out-of-Plane Fragility Curves of Historic Masonry Buildings and Implications on Risk Assessment, on regional risk assessment. So Valentina has a master's in structural and geotechnical engineering from the same university, and she is currently a PhD student in structural and geotechnical engineering under the supervision of Professor Fulvio. Valentina was also a visiting student at UCL during the last year, and she will explain a little bit on how her research is going on and how this can be integrated with the FaMIVE methodology. And finally, the last session is titled A New Procedure to Derive Typological Fragility Curves for Unreinforced Masonry Structure in a specific application to the Chilean case. This presentation will be delivered by Juan Pablo Muñoz. Juan Pablo is a structural engineering and he holds a master's from the Pontifical University, Catholic University of Chile. And he is currently working full-time as a researcher at the Research Center for Integrated Disaster Risk Management, CIGIDEN, in Chile. We also have here Chiara Palazzi, who is also a researcher in this same institution in CIGIDEN. She holds a PhD in architecture, structures, and conservation from University of Firenze, Italy. And all this project has also been developed with Professor Juan Carlos de la Llera from Universidad Pontificia Católica de Chile. He is currently the Dean of Engineering at this university. And all these projects, the one that we are going to see here and the one in the previous session from University of Naples have been developed together with UCL, with Professor Dina, and we are going to see how this methodology of FaMIVE can be implemented in real case studies. So without further ado, I think that Ariana, the floor is yours now. Thank you all for connecting, and please feel free to ask all your questions through the Q&A. Also in the chat, we will have the possibility to discuss, but the idea will be to have all the questions in the Q&A. So once Ariana finishes, she can start answering all the questions. At the end, we will have some time for live questions and answers. Thank you all, and please, Ariana. You're muted.
I'm not sharing my screen yet. No.
Now we can hear you, but we cannot see your screen.
Share this. Now, can you see my presentation?
It's loading probably, but it's not coming up yet. No. It's not loading. Before we saw it for a very short time, but now it's not loading, Ariana. Can you hear me? Ariana?
Can you see me or hear me or something?
Yes, we can now hear you. We can now hear you, but
yeah. Zoom decided I should go out. Sorry.
What? Why?
I don't know.
Okay, now we can hear you. Now please try to share the screen.
Okay. Share. Can you see my screen now?
No, it doesn't seem to load. Maybe I can share it at this end.
Now
yes, now it's sharing. So please go ahead.
Can you see my screen?
Yes. No, it doesn't seem to work.
And you are now muted, Ariana.
You are muted. You are muted. We can see your screen now, but you are muted.
Now, can you hear me?
Yes, and we can see the screen. So
perfect. So I'm presenting. Okay. Thank you. Thank you, Rafa. Sorry for this inconvenience. And hello, everyone. My presentation is about the seismic assessment for the urban heritage, the case of the Pla de Remei in Valencia. Pla de Remei is part of the 19th century extension, this part in red, of the old city center of Valencia, which is this part in the map. Is part of the artistic historical site of Valencia Historic Center and was declared a set of cultural interest in 1993. This area where most of the Valencian modernism is located was developed between 1884 and 1950 after the demolition of the medieval walls, and it's formed by 20 blocks. Residential blocks form one grid organized with white chamfers, as you can see in this picture, following the urban model proposed for Barcelona. Analyzing the historical maps of the area, we can see here in the map of 1869 that at that time there were just fields and farmhouses. Here we can see the trace, well, the medieval walls at that time. And we can see in the maps prepared by Taverner and Broseta that the area was developed in very short time, being at the end of the 1950 totally built. Here in the timeline, we can see the date of the demolition of the walls, the date of the approval of the urban plan for this area, 1887, the Spanish War, and the date in which this area was declared a set of cultural interest. This study is focused in the 205 masonry residential buildings, those in violet in the area, built before the end of the Spanish War in 1939, and being safe from demolition, still remain in the area. We can see here in the timeline, this is the period in violet that we are going to study, with the date with the demolition of the medieval walls. And this part in gray correspond to the years in which these buildings in gray were demolished and substituted for new modern buildings. According to the Special Protection Plan, only 9% of the buildings that we studied were not listed in any grade. Considering the heritage value, the main objective of this study was to determine the seismic risk to support decision-making in terms of minimal necessary retrofitting. For this purpose, the first task was to identify the assets of risk, including the definition of the urban, architectural, and heritage values. This task was done through a fieldwork, consulting the cadastral database, visiting the historical archive to check the original drawings of the buildings, analyzing the catalog of the Special Protection Plan, and studying the original urban planning regulations of the area that at that time focused on for the first time on natural light and ventilation. And here we have some drawings from these regulations, where it was established the height of the ground floor, the total height of the different facades, the number of floors. So they were quite rigid regarding the number of floors, inter-story distance, total height, size, and layout, etc. So here we can see in this picture some of the facades of the area, that despite the variety of architectural styles, the layout of the facades are quite similar. Regarding the structural characteristics, the study of some original drawings allowed to assess the construction and structural system of these buildings that were designed to withstand only gravity loads. The main characteristics are regarding the vertical structure and reinforced brick masonry bearing walls, facades, staircases, and party walls. Inner brick columns, as we can see in this picture, this is a party wall, this is part of the facade, and one-way horizontal structures with timber here, or steel joist and light tile walls. An extensive on-site survey allowed to identify the variability and uncertainties regarding the floor typologies. Some of them were steel, some timber, but some of them were strengthened floors with a concrete slab. The thickness of the bearing walls, that could be 360 mil if they were built with one stretcher and one header of standard bricks, or 480 if they were built with two stretches. And finally, the presence or absence of tie beams, because according to literature, the joists rested directly on the bearing brick wall. However, evidences of what seemed to be tie beams were seen during fieldwork. With all the retrieved information, a detailed building database was created, integrating urban, construction, structural, architectural, and heritage details. And this new database was analyzed in detail to identify criteria for grouping the 287 facades in order to select a reduced representative sample of the building stock to be analyzed with FaMIVE. It's important to point out that despite being possible to analyze with FaMIVE all the buildings in the database, considering the number of the buildings, the purpose of this approach was to show that representative samples can be identified for assessment of much larger building stock, and sensitive analysis can be conducted for uncentered parameters. On the other hand, as has been said, this sample can be considered quite homogeneous due to the limited flexibility of the planning regulations regarding the number of stories and the height between floors, and considering the reduced structural typologies available at that time. The criteria for selecting the elements of the reduced sample were first, buildings with reliable information regarding the dimensions, thanks to the original drawings consulted in the historical archive or the information included in the catalog of the Special Protection Plan. Then, a proportional representation of number of floors and number of openings. Both parameters are related with the slenderness. And finally, a proportional representation of the position of the facade in the block, considering three types. Inner facades connected with party walls with right angles, 90 degrees, as those, where's my mouse? Those here. We have C1 chamfer facades connected at one party wall with one right angle, that we did this one and that one. This is the right angle. And C2 chamfer facades connected with both angles greater than 90 degrees. The position of the facade affects the restraint offered by the side walls to prevent the out-of-plane failure of the facade. So it was important to know the condition for each of the analyzed facades. Then this reduced sample was used as an input data to FaMIVE to identify the different typologies representative of the buildings of Plat de Remei. We selected 43 buildings, 59 facades, and the uncertainties have been accounted through a sensitive analysis, assessing each facade several times, assuming the possible permutation of the unknown structural characteristics. That is, the thickness of the bearing facades, 360 mm or 480, the type of floors, timber floors, steel floors, or stressed floors, and the existence or not of the tie beams. At this point, FaMIVE was tailored to represent the specific characteristics of the sample, horizontal structures, the additions above 5th and 6th floor, the variability of the stories height, and the state of conservation. The results of this initial analysis, that were the collapse load factor and the failure mechanism, allow to obtain the capacity curves with the capacity assessment routine of FaMIVE, considering the collapsing part of the facade as a non-linear simple degree freedom oscillator, and these linear capacity curves were calculated for floors 5 and 6 floors. Then homogeneous subsets of curves were created considering the different number of stories, 4, 5, or 6, the presence or not of tie beams, and the two nominal thicknesses that we were considering, 360 and 480. And for each subset, a multivariate analysis was conducted considering the position in the block, inner, C1 or C2, the number of openings, the length of the facade, slenderness of the facade, slenderness of the piers, and as a result of this analysis, finally 14 typologies were identified as representatives of the building stock. Average capacity curves were obtained for the 14 typologies, considering, so we have 4 sets of capacity curves, considering 360 mm, 480 mm presence or not of tie beams. And then the fragility analysis routine of FaMIVE, based on the N2 method, allowed to obtain the fragility functions from the average capacity curves. In this case, we considered the response spectra provided by FEMA, because by using these response spectra, the obtained fragility functions are applicable to other cities in Spain and to South of Europe. Once the capacity curves and fragility functions were calculated, each of the buildings of the database was classified into one of these 14 typologies, assigning to it the corresponding capacity curve and fragility function. In this study, Selena software was used to compute damage and losses scenarios. The input data corresponding for each building were obtained for the database, including the UTM coordinates, the built area in square meters, the type of soil according to the Eurocode 8, and they obtained capacity curves considering our different situations and the fragility functions. Additionally, 6 different seismic scenarios were considered, so we obtained 24 different sets of results. Damage probability for the 5 damage states, and given the heritage value of these assets, in considering that it was difficult to quantify the expected probable losses in economic terms, losses were computed in terms of mean damage ratio and built damage area. Okay, Selena is a different topic. Let's focus on FaMIVE, and the conclusions regarding FaMIVE are: after creating a detailed building inventory, integrating urban, architectural, geometrical, structural characteristics and heritage value, a detailed analysis of the database allowed to identify criteria for selecting a reduced sample to conduct seismic capacity and fragility assessment. Then the reduced sample was analyzed with FaMIVE to obtain the collapse load factor and failing mechanism. The capacity and fragility routine of FaMIVE was used to correlate the collapse load factor and capacity curves to architectural and structural characteristics to identify homogeneous typologies. 14 representative typologies were identified, considering the number of stories, the position within the block, and the number of openings. And finally, capacity curves and fragility functions were produced to each typology with the capacity and fragility routine of FaMIVE. Regarding the results, despite Valencia being located in an area of low to moderate seismicity, the results show that the maximum percentage of built damage area ranges from 5.8% to 11.6% for 475 years return period, increasing to 33.59% to 51.59% for 975 years return period, which is important considering the heritage value of the buildings of the area. The high level of resolution of the study allows mapping and identifying the structures at higher risk, and is therefore a valuable tool to support sensitive and target retrofitting policies. You will find more information about this study in the paper Performance-Based Probabilistic Seismic Risk Assessment for Urban Heritage, an example in Plan de Remei area, Valencia, published in the Bulletin of Earthquake Engineering. And to finish, it is important to point out that at the end of the 19th century, the model of the expansion of most of the European cities was established by Haussmann in Paris during the Second Empire, which means demolishing medieval neighborhoods and building new healthy quarters. In Spain, at the end of the 19th century, several Spanish cities demolished the walls and expanded their old city centers, following the same new urban theories regarding the light and the natural ventilation. Therefore, it's possible to assume that some of the identified typologies can be extrapolated to other expansion areas in Spain of Europe. Thank you very much for your attention.
Thank you very much for the presentation, Mariana.
Thank you, Rafa.
If anyone has any question, please feel free to ask in the Q&A section. Now we will give the floor for Professor Fulvio. Please proceed.
Thank you very much, Rafael, and good afternoon, everyone. I'm now going to share the screen, but it is not possible. If you can allow me to share.
Yes, Ariana, could you please stop sharing? Thank you. I think that now Fulvio, you can.
Yes. Thank you. Thank you very much. Can you see it?
Yep, perfect.
Perfect. Thank you again. I am Fulvio Parisi from University of Naples, Federico II, Italy, and I will first of all shortly give you an overview about the macro-element analysis for global seismic response, but also fragility assessment of historical masonry buildings. And then I will leave the floor to Valentina Bonocunto, who will show you how this type of analysis can be incorporated effectively with FaMIVE analysis in order to account for both in-plane and out-of-plane failure modes. Then, first of all, I would like to show you some statistics about the distributions of masonry buildings, but also masonry types within several classes, with a special focus on historical buildings located in Italy. On your left-hand side, you can see, for instance, the distribution of the several materials within the Italian building stock. And here you can see that more or less 2/3 of the buildings in Italy are made of masonry. As we can expect, and also based on some statistical databases available for Italian masonry buildings, you can see also here that we have a non-uniform distribution here of masonry buildings with respect to their type of masonry. So we can see here that most of the buildings, at least 1/2 of the buildings, are made of irregular masonry rough stone. But the problem is that if we downscale our problem to some regions, we have a rather different situation where we can see here, for instance, on the bottom of the slide, that the distribution regarding the masonry type strongly changes. And so this, first of all, indicates us that we should have a higher resolution of our statistical data collection in order to better estimate at territorial level what is the level of risk. And so this drove us to further focus on some regions. For instance, here you can see one of the selected regions, which is Campania region in south of Italy, where we have that even 60% of masonry buildings are made actually of a different masonry type with respect to that I showed you before, because we now have a regular masonry type opposite to the irregular masonry type that we saw before. So another important aspect in relation to the statistical characterization of the buildings is related to their age of construction, because here we can see the different distribution of buildings over time. And this is strongly important because together with statistics related to the size of the buildings, for instance, in terms of the number of stories, we can incorporate this data in our subsequent analysis in order to bound our risk assessment with respect to the actual characteristics of the built environment. And so what is the methodology that we delineated in cooperation with the group of Professor Dina D'Ayala at UCL is basically an incorporation of in-plane and out-of-plane failure modes of the wall systems that provide the most of earthquake resistance to this type of buildings. And so, first of all, after collection of data, we processed them into a statistical way in order to then decouple the analysis in terms of nonlinear static analysis for global response of the buildings, but also nonlinear kinematic analysis for the identification and assessment with respect to out-of-plane failure mechanisms. So then we integrated this kind of analysis into a single assessment of capacity curves and fragility curves in order to derive some integrated IP-OOP fragility curves. So first of all, I would like to show you what is the basics and fundamentals of our analysis to account for global response of the building. We accessed it in terms of equivalent frame modeling. Then the approach is basically based on the graphical modeling in 3D of the wall systems. Then we go to the equivalent frame modeling of the wall, accounting for the possible different types also of floor systems. And then we further downscale the problem with respect to the type of modeling that we use for single structural elements. And this is why I would like to stress that we use a fiber-based modeling approach for each element of the wall. So this type of beam element, it's basically a Timoshenko beam element, so it is also characterized by shear and rocking behavior modes in addition to the main flexural one. And then we divide this Timoshenko beam element into 3 segments. 2 of them are rigid in order to incorporate the effects of pier-spanner interaction zones. And the central part that you can see here is basically consisting of a flexible element representative of either a pier or a spandrel of the wall. Then we discretize each macro element in order to account, as you can see here, for the macroscopic behavior of masonry. So we go beyond some phenomenological modeling approaches that directly provides you some, let's say, shear versus drift relationships for the entire masonry walls, because we account for the mechanics of this kind of behavior. And then we are able to integrate and incorporate all these features in order to simulate situations like this one, where we first of all accounted for some pushover tests in order to validate our modeling approach. Then we compare our numerical curves in terms of shear versus drift behavior with respect to the experimental curves. As you can see here, we have a very low level of statistical model error over the whole range, I would say, of drift demands. So we are able to account for different types of failure modes in the plane of the masonry walls. But also we performed a multi-scale experimental validation in order to account also for the interaction between the peers and spandrels. So this is why we use some experimental data sets regarding some pushover tests on full-scale walls with openings. Here you can see one of them, one of those specimens, which was characterized by a soft stone masonry together with some wooden lintel above the central opening. So this was a symmetric wall system. And then on your right hand side, you can see here the numerical experimental comparison in terms of pushover curves. Again, you can see here that we have a very good level of agreement between these kind of course, also because we are able here, for instance, to account for some shear flexure interaction that in some cases strongly affects the final behavior of this kind of systems. So we went ahead with an application of this modeling approach to a region of interest, which was the Campania region. We also selected an age of construction. Obviously, you can reproduce this kind of analysis over time and also for other regions of interest. And then we also selected a masonry type. So based on these three assumptions, we disaggregated the data set in terms of a number of stories and type of floor systems. And then we also performed an uncertainty modeling of the mechanical properties in order to incorporate directly them, all of them, within our analysis. And so we, according to the distribution of the actual built environment, we simulated the different amount of buildings according to the number of stories, as you can see here, then simulated more or less 1,700 buildings in the region. Then we selected a suite of ground motions, of real ground motions as per FEMA P695 guidelines. So here you can see that we accounted for also what we typically call a record-to-record variability. Here you can see that, for instance, if we pick up this fundamental period, we are able also to address the sectional distribution of the pseudo-acceleration demand on the buildings. And then here you can see that the dispersion of this kind of probabilistic distribution is quite high, as we know. So in this approach, we are aiming to mostly consider the record-to-record variability and what is the consequence of all the variabilities in relation to the geometry of the buildings, but also on the mechanical properties. And finally, we performed a global structural modeling of the buildings, then aimed at developing a vulnerability model which is based on the peak ground acceleration as an intensity measure. Then we integrated this approach into a nonlinear static framework for the global response analysis of the building. Here you can see also a typical plan of these buildings. And then we finally got the global capacity curves of the buildings. For instance, here you can see the capacity curves related to the X direction of the building plan under modal force profile, but you can see you could see also some similar outputs related to other directions of the building and other force profiles. So we characterize the dispersion associated with the number of stories over the whole range of drift capacities. And then we identified for each pushover curve here the occurrence of 4 damage states, DS1 to DS4, then going to from operational level to a collapse prevention level. And then according to this basically macro modeling approach, we then also derived the fragility curves associated with the in-plane failure of masonry walls. So here you can see the variability of the fragility curves. Again, if we start from single story structures and then we go to the case of 2 stories, 3 stories, and finally 4+ stories. And what we can say here to briefly conclude this first part of the presentation, you can see here which is the variability related to the median mu, median PGA across different damage states, but also across different numbers of stories of these buildings. And on your right-hand side, you can also see the variability of dispersion. Then we can say that the median PGA strongly increases, more or less, even up to 4.2 times. When we go from DS1 to DS2, then increasing more slightly about 3 to 41% and 3 to 10% to reach DS3 and DS4 respectively. The dispersion strongly changes with respect to the number of stories, but also the damage states, then ranging in the interval 0.56, 1.12. And then the median collapse capacity, and this is a very interesting result, reduces as the number of stories increases. So this is a further confirmation of what we also knew in the literature after analysis on other types of buildings and other regions of interest. So thank you again, and I leave the floor to Valentina Buonocunto in order to show the second part of the presentation.
Yes, thank you, Professor Parisi. Give me a second for share my screen. See my screen?
Not yet, Valentina.
Not yet.
No, yet. Now?
Yep.
Okay.
Okay. Okay, thank you, Rafael, for your introduction. Good afternoon, everyone. My name is Valentina Buonocunto from University of Naples Federico II. And today I will explain how we applied the FaMIVE framework to obtain fragility curves for out-of-plane failures of historical masonry buildings, and then the results of the regional scale risk assessment, in particular for Campania region. We used FaMIVE to calculate the out-of-plane fragility curves previously shown by Professor Parisi. I briefly recall the underlying hypothesis. The modeling typology is rigid body modeling. The analysis method is nonlinear kinematic analysis, and for the masonry is modeled with infinite compression. Having all the mechanical and geometric parameters from the database, the collapse mechanisms were calculated for the wall under examination. Subsequently, the capacity curves we obtain through nonlinear static analysis. Here are shown these capacity curves for different number of stories, 1, 2, 3, and 4+. And damage states were also defined on these curves.
which are critical for understanding the magnitude of structural impact during seismic events. Specifically, we have 4 damage states, the DS1 to DS4. DS1 occurs at the change in stiffness of the capacity curves. DS2 at the first point displacement with maximum base shear. DS3 on the plateau in the middle about, and DS3 DS4 on the decrease break of the curves. Applying the N2 methods, we obtain the out-of-plane fragility curves for the different number of stories. As you can see, the median value in particular show a minor increase between DS1 and DS2. Followed by an increase from DS2 to DS3 and DS4. The transition from DS2 to DS3 is particularly evident, which could reflect the sudden onset of unique failure mechanism associated with the out-of-plane action. Following that, we combined the fragility curves for in-plane and out-of-plane failure using maximum likelihood estimation. The results are expressed in terms of median value and dispersions, providing a more complete risk assessments. And here are the median for the 3 case for 3 failure modes, in plane, out of plane, and the combination of the 2. We observe that the biggest medians for DS1 and DS2 are for in-plane failure, and while for DS3 and DS4 we have a bigger median for out-of-plane failure. Consider the combined curves, the median attenuated for all DS and for the number of stories, being in the middle between the in-plane and out-of-plane failure. Now I explain the procedure for risk calculation and impact modeling. We calculate 3 different metrics, where matrix 1 calculates the percentage of building that were usable, not usable for short time, from week to months, not usable for a long time, from months to years, and the percentage of building collapsed for different damage level from the DS1 to DS4. The matrix 2 evaluates the percentage used for computation of economical losses. So the percentage of cost of repair for different damage level. And the last one, the matrix 3, evaluates the relationship among damage level with fatalities and injuries. At the bottom, you can find the schemes for obtain the results in terms of damage and risk for the area of interest. The first scheme show the steps for calculation the risk. In input, we have a vulnerability and the fragility curves. I put this information in IRMA software, and we have in output the damage. This damage combined with these 3 metrics obtain the risk. The risk in terms of number of building, economical losses, and human losses. Now this slide shows maps for the Campania region derived for 50 years return period for DS3 damage. Shows the percentage of buildings that attained DS3 for 3 different failure modes, in-plane failure, out-of-plane failure, and combined for in-plane and out-of-plane failure. You can see that the area most affected are those located away from the coast, probably because there are more historical centers where there are more historical buildings, than on the coast. Similarly, this slide focuses on DS4, illustrating the percentage of collapsed buildings. But we compare with DS3, we note more buildings collapsed by out-of-plane failure. This is DS3, this is DS4. Here I studied the impact in terms of a percentage of buildings not usable for a long time. It can be seen that the percentage of not usable buildings is higher for buildings that have in-plane failure, and for combined in-plane and out-of-plane failure. And here the maps for the collapsed buildings. For all 3 failure modes, we have a damage concentration of collapsed buildings in the center and in the right of Campania region. For an unconditional risk over a 1-year time window, we have calculated damage, usability, human losses, and economical losses for 3 failure modes, in-plane, out-of-plane, and in-plane +1 out-of-plane. As you can see, economical losses are higher if failure are combined. This probably become from the high number of not usable building in the long time period have a out-of-plane failure mode. Anyways, for human losses in plane case, fatality and injuries are more than in out-of-plane failure. While for the case of combine the in-plane and out-of-plane failure, it is similar to the case of in-plane failure. Thank you for your attention.
Thank you very much, Fulvio and Valentina. Please.
Thank you, Professor D'Ayala. Thank you.
Yes, thank you, Valentina. Thank you, Fulvio. This was a very interesting topic, and it was very interesting also to see how the results from Valencia are related also with the results from La Campiña, and that we can see some typologies that are similar in the regions, and of course, considering we are in the Europe continent. Now we are going to move to another continent. We are going to talk about the specific case of Chile. For this, I will give the floor to Juan Pablo. So please proceed. Thank you, Juan Pablo.
Thank you, Rafael. I'm going to share my screen. Can you see my screen?
Yes.
Perfect. Okay. Thank you. Good afternoon, everybody. My name is Juan Pablo Muñoz.
Juan Pablo,
I work at CQN.
the presentation is in presenter mode. So if you
okay. Let me see how to change it. There it is, I think.
Perfect. Thanks.
Great. Thank you. Okay. My name is Juan Pablo Muñoz. I'm going to present our work, a new procedure-derived typological fragility curves for unreinforced masonry structures and application to a Chilean case. I'm presenting in the name of our team. Here present is also Nuria Chiara Palazzi, who is actually leading this investigation. Also part of the team are Juan Carlos Herrera and Professor Dina Ayala. So I'm going to start, with a bit of context to see why it's important to study this in the case of Chile. So we can see that Chilean unreinforced masonry buildings are quite important in terms of heritage structures. It's a topic of scientific interest because we can see very unique features in terms of architecture and construction techniques, and it's because it's a convergence of different construction cultures. Here we can see some examples of that. Need the pointer here. So there's an important variety of buildings of this type in Chile. Here we see, for example, colonial style buildings with this continuous facade and single-story building. It's quite different from this one in the middle, this two-story building, where you can clearly see the difference between different structures, and this neo-Gothic basilica in the center of Santiago as well. So from that point of view, from our heritage, from architectural point of view, it's quite interesting to study this because of its value. Now, if we see how these heritage buildings are distributed in the country, we can see that most of them are located in the central regions of Chile, which is where most of the population is concentrated actually. And most of them are in the metropolitan region, which is where the capital, Santiago, is located. So that's where we are going to focus our study. And obviously, these buildings are mostly, most of them are unreinforced masonry structures, which are very vulnerable to seismic hazard. And we have seen that in different earthquakes in the past. Here are just two examples of that. We saw that in the 1985 earthquake and also in the 2010 earthquake, where important damage was observed to many buildings, but in particular to unreinforced masonry buildings. These were strong earthquakes, megathrust earthquakes, magnitude 8 and 8.8, that caused severe damage. For the particular case of the 2010 earthquake, we saw, well, first, it affected the country in many ways. 500,000 homes were severely damaged. We saw important economic losses and an important number of deaths. But in particular, if you go and see what happened to the unreinforced masonry structures, we saw that 370,000 of them were completely destroyed, which meant that 500,000 dwellings suffered severe structural damage, leaving more than 200,000 families with a home. So that obviously is something important to take into account to justify it, so to speak, why we're studying this. So taking all these points, it's important to study this in the case of Chile because we have high tangible and intangible values from a heritage point of view, but also because it affects the people severely whenever there's seismic damage to these kind of structures. Obviously, because these structures, as I mentioned, are particularly vulnerable to seismic hazard, and also because, as we can see in some other studies, they're associated with high socioeconomic vulnerability. So it's important to study this in the case of Chile. And that being said, the main objective of the project that we are running is to preserve and value the minor heritage buildings of the historical neighborhoods and centers of the Central Valley of Chile. And for that, we need a seismic vulnerability assessment to being able to quantify the possible impact of earthquakes. Now, as I mentioned, most of the historical buildings in Chile are located in the central zone, so we are going to focus the study there. So here we have the country. If we focus on the metropolitan region here, then we focus in Santiago here, and then we focus on the center of Santiago here, we get to this zone. This is a typical zone. It's called the Yungay neighborhood, which is composed by unreinforced masonry aggregate structures. It has over 40 blocks composed by different materials. We have brick, we have adobe, and we have tabique, which is this combination of masonry and these wooden elements here. And this is the zone that we're studying and applying the FaMIVE methodology to obtain rigidity functions. If we take a look at the site we're studying, we have different kinds of blocks. We have basically three. We have the closed blocks, which are the original ones. This is just one single unit with different blocks. It has no division inside. But some of them were, over the years, intervened, and this inner pedestrian road was added inside. So it's easier for people to access their homes. This is the second kind of block, the penetrated one. And you can see that there's this road that doesn't divide the block into different pieces. But some of them were further divided into more than just one block, and that give us the divided blocks, which are, as you can see here in the map, they are not very, very common. Most of them are just closed. Some of them are penetrated, and just 4 of them are divided. Here we can see some examples of the facades that we are studying in the Yungay neighborhood. On the left, we see an example of closed block. We see this continuous facade with no opening for roads, just the windows and doors. Here in the center, we see one example of a penetrated block. So we can see here we have this inner pedestrian road, but we cannot get to the other side, to the other street, because there's a wall. This was introduced in the beginning of the 1900s when the cités were introduced. It's just a way of increasing the population density. And this is an example of a divided block where you can walk all the way through from one side to the other, because it's completely open on the other side. So essentially what happened here is that one wide block was transformed into different blocks with that are, as you can see here, more narrow. But also there's also a classification of the sites we're studying, not just in terms of blocks, but also in terms of the architectural features. We have mainly two main architectural styles. We have the colonial style derivations, like this one here, and these facades that we can see here on the right. And we also have the classicist and variant style that we can see here on the right too. I'm going to give more details just now. So for the first time, we have the colonial style derivations. This represents around 60% of the facades that we are studying. There are typically single-story buildings like this one. Sometimes there are two-story buildings, but it's not very common. They sometimes have this kind of addition on top of the facade called the techo. They have a wooden structure, wooden trusses for the roof. And one interesting element that is common in the Yungay neighborhood is the ochavo, which is this diagonal wall in the corner. Now, for the classicist and variant buildings, this represents 40% approximately of the different facades in the Yungay neighborhood. They tend to be two-story buildings, sometimes 3 or 4 stories, but it's not very common. Most of them are 2 stories. And when it comes to materials, we have a variety of them. Some of them are brick, some of them are adobe. Sometimes you found in the upper stories tabique. So there's differences, obviously, and that translates into differences in the capacity curves. This is just like one broad, so to speak, architectural style. You can see more specific detail in the architectural styles, like you find neoclassic, neo-baroque, and other kind of styles there. So that's what we're studying here, the Yungay neighborhood, and we are applying the FaMIVE methodology to obtain fragility functions that we can use for seismic risk assessment. Obviously, I'm not going into detail here because this was presented yesterday, but what we're focusing now is into part of this analysis, mostly the data collection. Obviously, we visited the facade. The sample was composed by 423 facades. We collected the data in the FaMIVE form. Obviously, this is updated, and we have to try the new shell to see how it works. And with that, we could run the analysis to obtain the capacity curves of all the facades and the controlling mechanism with which is an input for the next step where we can obtain the predictive functions that we can use then obviously for the seismic risk assessment. But not only we went to collect the data for the FaMIVE program, but we also collected some data to further characterize the facades in mechanical terms. So we ran some in situ testing. We got some samples from the walls, and that allowed us to run different tests. So we could characterize the facades in terms of the compression and tensile strength, but also in terms of the cohesion coefficient between the mortar and the brick. That was used obviously as an input to characterize the quality of the masonry, but also we're using that for other studies for the facades. Now, we ran the analysis with FaMIVE, and what we observed was that most of the facades presented an out-of-plane failure mechanism. In particular, most of those were this mechanism here, mechanism E, where you see this overturning of this piece of the facade due to damage the spandrels. The second most common mechanism was with 20% was the combined mechanism, where 75% of those correspond to this mechanism here with damage to the orthogonal wall. And 19% of the failures corresponds to in-plane mechanism, where now again there's one mechanism that is more prevalent among them, which is H2, with this shear damage spandrels here. And the interesting thing is that this distribution is consistent with what was observed after the 2010 earthquake, where the most important mechanism was precisely this one. So that means that we are obtaining results that are consistent with the evidence. Now we ran the analysis for all the facades, and we obtained 423 capacity curves that we can see here. And as we can observe, there's an important variability in terms of the capacities, both in displacement and also in the shear. We see a huge dispersion. So it's obviously not appropriate to just take the median value of this cloud of capacity curves and use it as representative of all the facades, because there's going to be too much variability in the results. So what we decided to do was to, as others have done, to try to define typologies of facades. Basically, we want to classify these capacity curves in smaller sets that are more consistent. So the first way of doing that was to classify them based on the failure mechanism or the family of failure mechanism that was observed. Here we see the median, the mean capacity curves for the different mechanisms that were presented before. And we see that there's an important change, particularly in the case of the shear coefficient. But we can also classify them in terms of the family of mechanisms. So we can have the out-of-plane, in-plane, and combined representative capacity curve. Now, while this works in the paper, obviously it's not something that's very useful probably, because we don't know, it's not easy to extrapolate these results to a different facade. If we go to a new facade that we haven't seen, we don't know beforehand if it's going to fail in an out-of-plane or in-plane or with a deep one mechanism. So it's not easy to use for a new setting. So what we wanted to do, what we wanted to obtain was, we wanted to obtain extrapolable results. So we decided to clusterize the curves based on their observable features. So we developed an algorithm to do that, and the goal is to build a logic tree that classifies the capacity curves based on these properties that we see here, based on the architectural type. And we have two different types, as I mentioned before. The floor type, if the elements are parallel or orthogonal to the wall, or if there are slabs. The quality of the connection between orthogonal walls, if they are good or bad in both ends of the facade or just in one of them. The number of stories. The roof type, because we see some facades, some structures have tiles, some have metal elements. If we have masonry or wooden parapets or just slab, the kind of additions that we have, because sometimes we have architecture, sometimes we don't, and the material of that architecture changes, and also based on the material, if we have adobe or brick, how how is the dimension of those elements, or if we have tabique. So we developed this algorithm that classifies the facades automatically based on these properties to get typologies, to get these clusters that are easier to identify. Here I'm going to zoom in a bit, but basically here we have the initial set of facades, and this classifies the facades first. It divides the group in two based on the architectural side. So here in this upper portion corresponds to the colonial derivation, and this lower portion corresponds to the classes and the variant style. And then it further divides this group based on different architectural features. And the goal of this is to try to minimize the variance that we see inside the cloud of capacity curves. So each new cluster, each new node of this logic tree has less dispersion than the one before. So if we see here, I'm going to zoom in. For example, here we divide the initial cloud in various architectural styles, as I mentioned. This one here, it's divided then based on the number of openings. So one branch has 1 to 2 openings, and the other one has 3 to 6. This is further divided based on the thickness of the wall, the thickness at the bottom. So we have one side with elements between 70 and 90 centimeters. The other one is between 20 and 60. And then it's divided, this one, based on the length of the wall. And the same is done here for the other side of the facade, and not necessarily the divisions are the same. For example, here there's a division based on the additions on top of the facade, or based on the number of stories. That depends, because the algorithm is adaptive. It adapts to the different. Each time you have to make a division, it selects the best possible way to do it, to minimize the dispersion. But we can also try and tell this program how to classify the facades based on expert criteria. So here, for example, this is based on engineering parameters. So the facades are divided based on the total height of the facade, the number of good connections, the thickness at the bottom, and the roof type. So it's a very flexible solution, and each end of the logic tree corresponds to one typology of facades that we get a capacity curve for a cloud of capacity curves, and we can obtain a median curve that is representative of something that is easy to go see a new facade and see where it goes. We just go to a new site, we see, okay, this facade has 2 stories, 6 openings, the thickness of the bottom at the bottom is 50 centimeters. Okay, this goes in this cluster. So it's very easy to extrapolate to new facades. With this, we're running the N2 method to get the fragility functions for each one of the clusters. These are initial results for a previous logic tree, not for the one that I showed just before. But we can see that between different clusters, we see differences between damage states. We see how the median value of the curve are changed significantly. Particularly if we see the damage state 4, we see that this one is different than this one, for example. So we're checking that to see that the structure that was obtained for the capacity curves is preserved in the case of fragility functions. So we're just at the stage of fine-tuning this logic tree to get the final fragility functions, and then we can run the seismic risk assessment. So those are basically the final steps of our research, and we're going to publish this very soon, just to define, to fine-tune and finish the definition of the clusters, to make the final definition of the fragility functions. We also want to combine this with empirical data that we have that was observed after the 2010 earthquake to obtain hybrid fragility functions. And then we want to run a seismic risk assessment, the Yungay neighborhood, to analyze then how many buildings are expected to fail, how many could be the number of injuries or the economic losses. Thank you very much.
Thank you, Juan Pablo. It was a very interesting lecture. I think that today we had the opportunity to see how this FaMIVE methodology can be integrated in different methodologies in different locations. We saw how in the latest presentation, how this was integrated into the risk assessment to identify losses as well. We saw the same in Valencia with the use of Selena and in Italy with the use of Irma. So I think that this is very, very good opportunity to bring all this experience here. So now I will give the word to Dina for some final remarks to close this webinar.
Thank you very much, Rafael. Well, I think we have, hopefully we have been able to show the breadth and depth of on how FaMIVE can be used to, first of all, define the vulnerability and the size, and eventually the seismic risk of buildings, of historic buildings, not just at the in the case of one isolated case, but at the territorial level. And we know that many city centers, exactly, not just in Europe, but across the world, have these very pressing issues. We know that masonry structures are responsible for very many deaths and injuries during earthquake, and therefore how critical it is to improve this part of the building stock. We also know that they are a large proportion, that they have a very large value of embodied carbon, and that they are a very important cultural value, and therefore we need to think very carefully about the best way of making use of this resource while ensuring the safety of the users and the inhabitants. In previous years and decades, very often these buildings were demolished and replaced. We now understand better what are the consequences of this type of interventions. I think that all communities in all culture around the globe really now understand the value of their heritage, and at the same time they understand the value of the energy that is embodied in this building, and what does it mean demolish and destroy them. So with that in mind, we hope that these aspects also is considered. I see that there are some questions maybe in the Q&A. If there is anybody that also would like to ask questions verbally, please raise your hand and open your microphone. We also, I welcome questions from the panels, because of course, while I've worked with all of you, you haven't worked, these three projects were developed separately, so there might be questions across the three projects and the three different approaches. So there is a question here. As I have observed from numerous presentations, FaMIVE works mostly with masonry structure. Can it also be applied in evaluation or reinforced concrete structure, or is there an alternative to that? There are many alternatives to FaMIVE to apply to reinforced concrete structures. Maybe not as systematic as we have presented this, but you can use many finite element nonlinear application. You can use OpenSeas, you can use Seismostruct to conduct the analysis, and then the derivation of capacity curves and fragility functions can follow the same approach that we have highlighted or similar approaches. You can look at the literature in that respect. Please, from any comments or any further exchange of questions from the panels, please.
Nina, I break the ice. So with the first question, with respect to the study by Juan Pablo, first of all, thank you for the presentation. It was very interesting. I was wondering if you accessed the variability of fragility curves with respect to, let's say, the intensity measure that you select, because probably depending on the sufficiency and efficiency of the intensity measure, integrated with the variability of the structures that you selected, you might also observe some variability in the fragility curves. So this is my question.
Yeah, thank you. Well, if I understand your question, yeah, it's because I think we're trying to reduce the variability in the capacity curves, but then we get some new variability when we go into the fragility functions, right? So yeah,
yes,
exactly. We are aware of that. What we're doing is we're obtaining the capacity curves, trying to reduce the variability in each typology. We get the fragility functions, and then we have to check if what we obtain it still makes sense, because maybe we have a tree that makes sense for the capacity curves, but then if we go to the fragility functions, maybe because of this new variability due to the earthquakes, to the hazard, some of these clusters needs to be combined into a new one. So yeah, we're still in that phase, but we're taking that into account.
Okay, thank you.
You're welcome.
So, yes, we have considered, to be more explicit, we have considered, Juan Pablo can also expand a little bit more on this, we have considered two different cluster of spectra that we test. All the fragility of all the capacity curves, let's say the cluster representative capacity curve against, and these are the P695. So it's a very large range of different spectra, which are not specifically associated with a particularly seismogenetic zone. So basically, they just have an ample spectrum of energy, PGAs, and everything, and we scale these over a large range. And then we are instead used a set of a similar number of spectra, but generated with reference to the specific seismogenetic zone of Santiago. So they are basically consistent to the local seismicities. And interestingly enough, we obtain quite similar results with these two set of spectra, while using the NTU method, but this is more down to the NTU methods than to.
Oh, okay. But was there any variability in the soil type, for instance, under Santiago? Or it is quite homogeneous subsoil?
I mean, in Santiago, yeah, you have a bit variability, but in that zone, no, it's quite homogeneous in that area. It's a good soil.
Consider that it's not a very large portion of it. It's maybe
exactly
1 square, 2 kilometers square. So it's not a very large.
Okay.
Area. Many buildings, but not a large area.
So quite densely populated area.
Yes.
Okay, thank you.
Instead, if there are no questions, let me see, there is maybe another question here.
Right.
Bashir, thank you very much for all your comments during the calls. Maybe you want to open your microphone and actually ask the question. And I also see that there is a raised hand by Kevin. Bashir, if you want to go first. Or do you prefer that I read your question? So Bashir is asking, why don't the countries most exposed to seismic risk oblige the owners and operators of existing buildings to reduce the seismic vulnerability of their property by means of regulation and financial incentives? Arianna, maybe you can give an interesting answer to this, considering the various studies, not just in Valencia, but more in general in Spain on this plan, and also Fulvio in relation to the Italian.
Well, it's quite difficult for the countries to oblige the owners of the buildings to do any analysis of the buildings. In fact, in Spain, it's compulsory for all the buildings that are older than 50 years, that they have to have some kind of assessment of the structure and environmental efficiency. But usually, unless the owners are see that some fine is coming if they don't do that, they try to avoid doing this, because in the end they have to spend money doing that. This in one hand. In the other hand, many times the owners of the buildings are not living in those buildings. They are just renting. So, of course, they are not interested in what could happen in the event of an earthquake. And this was the case we had in the earthquake in Lorca. After the earthquake, a lot of buildings were demolished, and we had some kind of money given to the owners to repair the buildings or to rebuild if they had been demolished, only in the case that these were the buildings where the owners were living, which was not the case. So in the end, a lot of people just became homeless without any place where to live, and the owners lost the property for sure, but also the opportunity to rebuild or repair their buildings, which was a pity. So I don't know how the policies should change, but at this moment they are not working, at least in Spain.
Well, in Italy, we have a similar situation. In addition to this one, we have a measured data to account for because more or less 80% of the population is also owner of at least one property. One apartment unit or even building. So the problem is also socio-economic, is also a socio-economic problem in relation to the expected cost for the retrofitting of this huge amount of buildings. So this is why in Italy the political the policy was to support the population through financial measures in order to push them and further push them to retrofit their buildings, but it is not it is not mandatory. Unless for static loads. So if you have a building or even a single apartment unit and it turns out to be at an insufficient level of safety under even gravity loads, then you are obliged to retrofit the building. This rule does not apply to the seismic safety. Also because we have a strongly non-uniform situation of the risk in Italy. So we have some clusters of urban centers along the Apennines, the central part, central hilly or even mountainous part of the Italian territory, where you have low levels of income, but they are dramatically associated with the high levels of risk. So that is the problem. Even more recently, there was a change in the policy regarding industrial buildings, because industrial owners are now obliged to activate some insurance programs.
Thank you very much, Fulvio. I don't know if Bashir is able, because he said he had some problem with his microphone. So if you want to comment on our responses, Bashir, please feel free to open your microphone if you can. Otherwise, I will ask Kevin if it's possible for Kevin to open his microphone and ask his question. Hi, Kevin.
Can you hear me?
Yes, we can hear you. Thank you.
Yes, I'm also dealing with something in this line in my
Yes,
research.
can you introduce briefly yourself and tell us where do you work, where you come from?
Okay, I'm Kevin Karanja. I'm from Kenya, but currently studying in Hungary
Okay.
at Eastern University. So my area of research is also on the seismic fragility curves in public buildings. So I've also asked that question in this here, but I can ask verbally. So is there a set criterion for determining the parameters that we use to determine the topology to assess? And also the confidence level of this, for example, maybe from the observations and images, because we find that sometimes it's difficult to get the designs, the actual designs from the engineers or from the authorities. What is the confidence levels with this type of assessments that are conducted just from observations and images?
Thank you very much, Kevin. I think maybe Nuria, we had so many discussion, and also Arianna, about how to identify the typologies. Maybe Chiara, you would like to answer this?
Yes, thank you. Depends of the type of building and the disponibility to access to the structure. In the case of Santiago and Yungay quarter, we have visit directly the structure, for example, for the masonry type, we can see directly the type of connection, type of partners of the walls, the structure of roof and ceiling, and we use different type of induction, like thermocameral photo, to see the connection between structural elements. So in the case of Yungay, we have a high confidence level for the type of the buildings and the visibility of the connections.
Arianna, I don't know if you want to.
Yes, I want to add. It's true that it's not always easy to have the original drawings with the dimensions. In this case, it was possible because the buildings were listed in some grade, and it was an area where the special protection plan had all the information about them. In other cases, it's always recommended to go to the area and do some kind of on-site survey, but maybe it's not possible to have to do it in all the area. Just have the data for some of the building, then you can estimate the data for buildings that are quite similar. So as we usually start doing this type of analysis is with the cadastral database. We can have on one hand how is the urban layout and how the dimensions of the facades and the number of stories we will find there, although sometimes there are some mistakes in the database. And then also the age of the building, because you can have more or less one estimation about the structural typology considering the age in which, the year in which it was built. And after that, with all the data that you have, you do your best. If you can measure, is perfect. If no, usually you measure 2 or 3 elements of all what you can do, and then extrapolate the data. If the building has a shop or public spaces in the ground floor, you can inspect at least a part of the building. And also we discovered that if you go for a walk in the area by night and lights are on, you are from the street, you can see sometimes it is possible, of course, the typology, the structural typology. You can see the timber joists or the steel joists from the street. Well, sometimes people have blinds and you cannot, but sometimes it's possible. And if you have one camera at this moment, just take picture and take data about the address or which building is it, so you can use the same data for similar buildings.
So as you can see, Kevin, one has to be quite inventive in that from that point of view. In terms of the uncertainty, in terms of the confidence, of course, the more the data is extrapolated, the lower is the confidence, and we try to take that into account in FaMIVE by having a reliability factor for each part, as you might have seen yesterday during the explanation of the shell. For each section of the set of information that we require, there is a different level of reliability that you can assume, and then on the basis of that, we take a range of because most of the entry requirement that we are asking you are related to let's say measurement or numbers. So we take a more narrower or larger range of possible values of these variables depending on the level of reliability, and therefore then all the results will also be affected by this range, as I tried to explain yesterday when I showed the results as well. So, of course, in the case, for instance, that Fulvio was showing earlier, and the case on which Fulvio and Valentina have worked, they have very large statistical information from which they have then generated as a fictitious sample of buildings. Maybe Fulvio, Valentina, you want to add a little bit on this?
Yes, we have a lot of data, and also we can change the resolution of the data. So according to what you said before, Dina, I totally agree with you that the resolution of the data will give you also different levels of confidence and reliability in the final results, either in terms of damage assessment, but also not only in terms of damage assessment, but also in terms of risk, and hence impact on the population, on the economic exposure, and even on the people. According to this problem, we can aggregate or even disaggregate the data based on also the level of information that we have, for instance, in terms of hazard. Because in some cases we have to downscale the problem in order to access some specific issues related to, let's say, for instance, local amplification of seismic ground motion, and this is why we pre-process the data in order to account for these aspects.
Yes, and there is always the opportunity to run sensitivity analysis on the data that has been collected, of course, to understand, in a reliability, let's say, more oriented approach, whether the output that you are getting is particularly sensitive to a typology with respect to another one, or to a particular construction detail rather than another one. And we have done some of this in the past, and again, you can find it in some of our literature. I don't know, Kevin, if you want to comment on our answers. Hopefully.
I'm okay with what has been said already. So I'll just maybe make some more research also in my area and try to incorporate what I've learned from.
Yes, please, and by all means, try to use FaMIVE or get in touch, and we can support you on that.
Thank you.
You are very welcome. There is a very interesting questions from Rabindra Adhikari. I don't know, Rabindra, if you want to open your mic and directly ask the question, please.
Yeah, I hope I am audible.
Yes, we
you.
can hear you. If you can introduce yourself and where you're from and which area you're working on.
Yeah, I'm Ravindra Adhikari. I am pursuing my PhD at Institute of Engineering, Pulsor campus, Nepal. I am working in stone masonry building. I see that there is a higher chance of falling off stone masonry outside the building rather than inside. But I do not know the chance. So in most of the case, the walls are falling in the street, but a few times we see it's falling inside. So for the house owners, it is risky if it falls inside, but for the outside people, it's more riskier when it falls outside. So is there any type of analysis we are doing to observe which chance is there? So in some of the retrofitting techniques also, I observed that the more focus is on preventing the tying the wall from outside. So if we consider tying from outside, then the chance falling inside is smaller, and that is it effective with smaller intervention. So I want to know if any work is done in this area, or if we are considering this in this application as well.
Thank you very much, Rabindra. This is actually very timely because three of us with another PhD student, so Fulvio, Arianna, and myself are really now working much more in details on studying the collapse, the mechanisms of collapse, or the way in which the collapse actually take place, and where the different parts that are collapsing end up to. I don't know, Fulvio, if you want to say something, and then maybe Arianna.
I leave the floor to Arianna, but afterwards I have something to say.
Yes, Arianna, please.
Well, as Dina said, is a very interesting question, because we are also interested in know how the collapse is going to happen. In some cases, because if it's an out of plane mechanism and all the facade will finish in the streets, then the streets will be blocked, and for all these works of rescuing people will be more difficult. So if you have to plan how to act in the event of one earthquake, you have to know which routes will be blocked and try to prevent this or have alternative routes. So yes, this is what we have in our hands at this moment, but we don't have the answer yet. I'm sorry.
Fulvio, you said that you wanted to add something?
Yes. Okay. First of all, the main motivation behind some provisions also for retrofitting of the buildings with respect to facades falling outside the building is related, obviously, to the possible indirect risk effect on the population, on the streets, and so on. Also on the resilience, or even on the resilience of at the urban scale. In addition to this, I would like to say that there is also a matter of type of method that you use for the analysis, and basically, if we run a nonlinear dynamic analysis, we could have some marginal probability to have facades falling inside the building. However, most of the probability of falling outside the building is related to some boundary conditions related to the presence of, let's say, floor systems, but also on the presence of some thrusting elements such as bolts or even pitched roofs. So this is why there is also a further action that applies on top of the facades that further stimulates the facades falling outside the building rather than inside. So there are several aspects to account for, and this is also why we are searching for some answers to this problem.
Yes, it might be worth also adding that, notwithstanding the facade falling out of the building, then of course the floor structures and the roof remain without support, and then they fall on they might be falling on the occupants. So while the occupants might not directly be affected by the outwards fall of the facades, there is also the risk of being affected by the collapse of the horizontal structures. But also maybe it's worth considering, and this maybe it might be seen more in let's say rural areas than in cities constructions. If the walls are made of rubble, masonry, and they are not very well tied together, they will not fall and collapse as a solid objects. They will tend to crumble, in which case there might be quite a consistent amount of material also falling inward rather than outward. And again, this is something that we have just started 3-year study on with the collaboration of the 3 universities. So we will probably organize a webinar on this in the next 6 to 8 months. So please keep in touch, Rabindra, and if you have results also let us know, because we would be very happy to hear from your experience. I don't know if you want to comment on our answers.
Yeah, thank you very much. Okay, yeah, I agree with Dina and all the participants. So this is still under study, and then for stone masonry, as Dina said, I do agree that if the elements do disintegrate, then there is chance of falling both way. But if it acts as an integral part, then most likely it will fall outside. So
Yes.
we may make some method to identify that.
Thank you very
Thank
much.
you, Alan. Yeah.
Thank you. There is another interesting question from Zishan Hamad. Zishan, do you want to ask your question lively? Please unmute yourself and introduce yourself.
Hello, ma'am. Hello, sir, Rafael, and everyone, sir. It was indeed very good session. I'm basically a PhD student. I'm also working on the risk and vulnerability assessment of RC frame structures using the infill walls. Practically, I'm modeling different buildings with this opening. Normally, when we model in laboratory, we just give the opening, and but in fact, in reality, if you see, the opening has some windows, they have some frame, and similar for doors and the glass that we have. So I wanted to elaborate if this is a very good software that's been introduced. In future, if these effects can be incorporated so that we can arrive at a very realistic study based on the experiment. I would like to have your views on that.
Thank you very much, Zishan. Yes, as I have explained a little bit yesterday, I don't know if you were online, we look at the distribution of the opening to understand what we call the isostatic flow of stresses within the walls, both vertically and horizontally, and also the different stiffnesses of both the piers and spandrels, and that distribution of the geometry and therefore the materials and therefore the stiffness and the state of stress for gravity load and then for lateral load tell us a lot in the way in which eventually the building responds or the facade responds, both in terms of in plane and out of plane. Further to that, in our collection of information, we also ask information about the lintels. And we also, because the lintels, of course, depending on how stiff they are and depending on how extended they are beyond the opening, they can have a further effect in redistributing the gravitational loads and therefore this state of compressive stresses in the pier. And also they tend to have a benefic effect on stiffening the spandrels. So that's why we ask that particular questions in FaMIVE. In a previous version, a few years ago, where we were doing an assessment in Lisbon, many historic buildings in the historic center of Lisbon not only have lintels made of stone, but also they have the frame of the window made of stone. And in that case, it might become a frame within the wall, and indeed can have a further effect in resisting lateral forces. So we also incorporated that. But in a more recent version of FaMIVE, we don't particularly have taken that into account because we haven't seen that characteristics. But as I said, FaMIVE is quite flexible, so we can add or remove particular effect or particular construction details that might have effect on the seismic response. I don't know if that answers your question, Zishan.
Yes, ma'am. Thank you very much. Looking forward to in the future.
Yes, please try to use it even with your infill walls and let us know how it works.
Sure.
And yes, we should nod to Ciro Canditone, who's the PhD student that is working with us on the issue of on the type of collapse and the fall of debris of following earthquakes. He has very kindly added some information in the question and answer chat, so please take note, Bajindra, if you want to look more into it. We have a question for Karima. Karima, would you like to introduce yourself and please ask your question? We can see that you have, but you need to open the microphone, Karima. Yes.
Hello.
Yes.
Do you hear me?
We can hear you. Yes, please introduce
Okay.
yourself.
Hello, everybody. Thank you, Professor, for your presentation. It was very useful for us. So I am a teacher in University of Blida, one in from Algeria. I am a doctor in architecture and specialized in built heritage and seismic risk. So my question, it was about identification of mechanical parameters of masonry. If you use in situ instrument or experimental to identify this parameter, or you just refer to existing or similar buildings to identify this parameter?
Thank you very much, Karima. I think that again, Arianna and Chiara would be best placed to answer this question in relation to the three to the examples that we have shown today.
Well, regarding Valencia, we don't have any experimental essays, but we went through the building codes on force at the time that the buildings were built. So we had some references to use regarding the properties of the masonry, the brick masonry, and also we measured the dimensions of the bricks in situ in some of the buildings that were possible to do that, and the thickness of the bricks and the joints to characterize the masonry. They were just theoretical values. We don't have any tests. We didn't have the opportunity to do them.
In the case of Yungay in Chile, we have had different experimental tests, like compression test of brick and mortar, the Brazilian tests on brick and mortar to evaluate tensile strength, and shear adhesion on brick and mortar to evaluate cohesion coefficient.
So yeah, so Karima, as you have, so we have in some case we have had the opportunity to do the test, in some others we haven't. As you might have seen during the presentation yesterday, we have a a set of predefined typologies for the masonry, for instance, with values of both the friction coefficient and the cohesions. The positive aspect of the method is that it doesn't need so many information about the material characteristics, because we are looking at the ultimate capacity of the material, and we know that masonry as it is fails mainly in due to shear. So we are looking at the let's say friction coefficient and the cohesion to see when that shear failure or shear strength is overcome. In that respect, there is a lot of past literature, especially in Italy. Many researchers in the past 20 to 30 years have gone through a lot of testing of masonry assemblies. The limitation of the experimental tests is that if you're looking at historic material, it is very difficult to extract materials from the structures and test it because of the historical value. And in that case, if you reproduce the material, then you need to use new mortar. And when you use new mortar, you alter the level of cohesion that the material inherently has. So you need to then recreate these assemblies, but then you need to maybe do some aging. You need to, especially with lime mortar might take, you know, years to develop its maximum strength. So it's a very complex element of it, and very often this is resolved by saying that the masonry doesn't have any tensile strength or any shear strength, but in fact it's that little strength that is indeed there that prevents it from failing, and that gives it the capacity to resist some seismic action. So that's why very often we ended up using values that are available in literature and that we know that are sufficiently reliable. But yes, all of us should be trying to do more in situ tests, like has been the case for Chiara's studies, where they had the opportunity to do those tests. I don't know if that answers your question, Karima.
Okay, thank you. It was very clear for me. Thank you. I hope I see you in another webinar or another conference.
Sure, welcome.
Okay, thank you.
I don't know if we have more questions. Otherwise, yes.
Yes, Dina, you have one more about FaMIVE and damaged buildings.
It is possible to analyze using FaMIVE a partially damaged heritage building which is still standing. Further, can the analysis results be used to suggesting retrofit measure? The very short answer, this is an anonymous attendee, so I don't know if you want to open yourself, your microphone and mention this, or I'm happy to answer it. Yes, as yesterday we didn't actually dwell on the issue of the damaged buildings, but there is an opportunity to collect the information in FaMIVE about the, first of all, about the level of damage of each facades, the type of damage, and the extent of damage. Naturally, the possibility of using the any calculation approach to determine the residual capacity of a building that is already damaged depend on the extent of damage that we are that is observed, and we need to make some assumptions in relation to, for instance, the presence of cracks, whether they are passing through the wall, whether they still afford the transmission of some shear stresses or compressions or compressive stresses through the wall, so that for instance, the gravity load can be transferred to the ground, and so on. So in a short question, in a short answer, yes, but each case needs to be looked in detail in order to understand to which extent the FaMIVE is applicable. In terms of the analysis results can be used for suggesting retrofitting measures, certainly. As I mentioned again yesterday, we will soon, probably in the autumn, have another webinar on retrofitting methods for masonry structures, where we will talk more extensively about this. But once we identify the mechanism of collapse, then we can also think as engineers on how to prevent them. And the way in which we can prevent them determines the type of retrofitting and the type of design that we want to do to ensure that the mechanism doesn't occur. So the definition of the mechanism is the first step towards the design of the retrofitting. And then once we have designed the retrofitting, we basically change the constraint conditions between walls so that they don't fall apart. We can then reanalyze the structures using FaMIVE or using more in-depth type of analysis to ensure that the strengthening that we have designed is working properly. And with this, I think that we have no more questions. Is that correct? So, Rafa, maybe you would like to close the session?
Thank you, Dina. No, I just want to thank you all the panelists. Thank you, Fulvio, Valentina, Juan Pablo, Ariana, and Chiara, and of course, Dina, for hosting this seminar. Thank you all attendees for connecting, and looking forward to see you all in the next webinar.
Yes, to mention that we will have one next for the first week in June.
Yes, we are planning to have one webinar the first week of June in collaboration with Miyamoto International about vernacular constructions, which is also very related to the activities of the chair. So we hope to see you all there. Registration will open hopefully next week.
Okay. Thank you very much. Thank you to all attendees, and thank you to the very stimulating set of questions that we have received. And we hope that you are enticed into using FaMIVE and telling us how it works, if it does, for your personal problem. Thank you very much all.
Thank you very much.
And thank
See
you.
you.
Thank you.
Yeah.
Goodbye.
Bye bye, everybody.
Bye. Bye.